If you strip away infrastructure, platforms, and applications, what ultimately matters to your enterprise? Data. Customer data, financial data, operational data, intellectual property, strategic documents, telemetry and analytics. Attackers do not break into your systems just to explore your network. They are after data. Regulators do not fine you because a server was exposed. They fine you because sensitive data was mishandled. Executives do not lose sleep over infrastructure complexity. They worry about data breaches. As an enterprise security architect, you must design protection around data, not just around systems. Data security architecture is about ensuring that data remains protected, at rest, in transit, in use, across environments, across jurisdictions, across its entire life cycle. If you design infrastructure without focusing on data, you protect the shell but not the core. You cannot protect what you do not understand. Data classification is the foundation of data security architecture. You must define what types of data exist, how sensitive is each type, what business impact would exposure create, what regulatory requirements apply, who owns the data. Common classification TS may include public, internal, confidential, restricted, highly sensitive. But classification must not be theoretical. It must drive architectural decisions. For example, highly sensitive data may require stronger encryption standards, limited access controls, segmented storage environments, enhanced monitoring. Public data may require minimal restriction. Without classification, security controls become uniform, either overprotecting low-risk data or underprotecting critical data. As an architect, you must ensure classification integrates with identity access models, cloud storage policies, DLP systems, logging standards, compliance reporting. Classification becomes the policy driver for control strength. Encryption is a critical component of data security architecture. But encryption is not just enabling a checkbox. You must define an encryption strategy that answers which data must be encrypted, where must encryption occur, what standards apply, who controls encryption keys, how is encryption enforced consistently. Data at rest encryption protects stored data from unauthorized access. Data in transit encryption protects data during communication between systems. For example, when sensitive data travels between applications and databases, transport layer encryption ensures confidentiality. When stored in cloud storage or databases, encryption at rest protects against unauthorized access to storage media. But encryption alone is insufficient if key management is weak. Encryption without governance is illusion. Architecturally, encryption must be consistent across on-prem systems, cloud workloads, backup storage, SaaS integrations. Inconsistent encryption standards create weak links. Your role is to standardize encryption policy across the enterprise. Encryption is only as strong as its key management. If keys are stored insecurely, rotated infrequently, or shared improperly, encryption fails. You must design a key management strategy that includes centralized key vault systems, role-based access to keys, key rotation policies, separation of duties, auditing of key usage. For example, application developers should not have unrestricted access to encryption keys. Operations teams should not bypass key management policies. Key management must integrate with identity governance. In cloud environments, native key management services offer structured control, but only if architected properly. You must ensure keys are not hard-coded into applications. Key rotation is automated where possible. Privileged key access is monitored. Backup keys are secured. Key management failures have caused significant breaches historically. As an enterprise security architect, you must treat key management as a critical control domain. Data protection often focuses on storage and transmission, but data is also vulnerable while being processed. Data in use can be exposed through memory scraping, privileged misuse, insecure application logic, excessive data access. While protecting data in use is complex, you can reduce risk by enforcing least privilege access, monitoring abnormal data access patterns, limiting bulk data exports, applying behavioral analytics. Architecturally, data access must be contextual, logged, restricted, aligned to role. Data access should not be broad simply because it is convenient. You must design access pathways deliberately. Modern enterprises operate across SaaS platforms and cloud environments. Data flows beyond traditional boundaries. Data loss prevention (DLP) helps detect and prevent sensitive data from leaving controlled environments. Cloud Access Security Brokers (CASB) provide visibility and policy enforcement across cloud applications. As an architect, you must define which data types require DLP monitoring, where DLP policies should be enforced, how CASB integrates with identity and cloud platforms, how alerts integrate with SOC. For example, if highly sensitive financial data is uploaded to unauthorized cloud storage, DLP policies can detect and block the transfer. If users attempt to share confidential documents externally, CASB controls can enforce sharing restrictions. DLP and CASB must align with classification strategy. If classification is inconsistent, DLP policies become ineffective. Architectural alignment between classification, identity, and cloud monitoring is critical. Global enterprises face increasing regulatory pressure regarding data residency. Different jurisdictions may require local data storage, restricted cross-border transfers, specific encryption standards, audit capabilities. Data residency challenges require architectural foresight. You must design region-specific storage strategies, controlled replication models, legal review processes for data movement, compliance-aligned encryption controls. For example, if customer data must remain within a specific country, cloud deployment architecture must reflect that requirement. Data replication across regions must be governed. Failure to address residency proactively leads to regulatory exposure. Data architecture must align with legal and compliance teams. You are not just designing systems, you are designing regulatory resilience. Data security architecture cannot operate in isolation. It must align with identity access models, cloud security architecture, logging and monitoring strategy, network segmentation. For example, highly sensitive data storage should integrate with strong conditional access policies. Network segmentation boundaries, privilege access governance, centralized logging, data classification should inform access policy strength. Encryption standards should integrate with key management systems. DLP alerts should integrate with SOC workflows. Architectural integration reduces gaps. Executives require measurable assurance. You must define metrics such as percentage of sensitive data classified, encryption coverage rate, key rotation compliance rate, DLP incident trends, data access review completion rate, residency compliance coverage. Metrics convert architecture into visibility. Visibility builds executive confidence. Without measurable progress, data security initiatives lose support. When data architecture fails, consequences are severe. Regulatory fines, class action lawsuits, brand damage, operational disruption, executive accountability. Data breaches often originate from over-permissioned access, unencrypted storage, misconfigured cloud services, unmonitored data exfiltration. These are architectural weaknesses. Strong data security architecture reduces probability and impact. Weak architecture multiplies risk. Data moves through stages: creation, storage, usage, sharing, archiving, deletion. Your architecture must define controls at each stage. For example, during creation, apply classification automatically. During storage, enforce encryption and access controls. During usage, monitor and restrict abnormal access. During sharing, apply DLP policies. During archiving, ensure secure retention. During deletion, enforce secure destruction policies. Lifecycle thinking prevents blind spots. Data protection must persist from cradle to grave. Ask yourself, do you know where your most sensitive data resides? Is data classification driving access controls? Are encryption and key management standardized? Are DLP and CASB integrated architecturally? Are residency requirements embedded in cloud design? Is data protection measured consistently? Data security architecture determines whether your enterprise controls its most valuable asset or merely hopes it does. Protection must be intentional. Protection must be consistent. Protection must be lifecycle driven. If this lecture helped you understand how to architect data protection strategically, make sure you subscribe to this series. In the next lecture, you will explore security operations architecture and how detection and response integrate into enterprise design. Like this video if you found it valuable. Comment below and tell me, does your organization truly know where its sensitive data is? Your journey toward mastering enterprise security architecture continues in the next session.